So welcome to this video on Time Resolved Microwave Conductivity in reality. Today what we're going to be talking about is generation of microwaves and the electronic components to do so. So in particular the microwave source. So last time we talked about the basics of Time Resolved Microwave Conductivity. We viewed the system in a very simplified form where we just had this microwave source and detection circuits, which we didn't really talk about in too much detail, other than we knew that it was capable of producing microwaves or an electrical signal in the microwave frequency regime, and also capable of detecting the intensity of reflected microwaves. And that's the principle of the experiment. By disturbing the carrier concentration in a semiconductor with an optical laser pulse, we're able to change the reflected microwave intensity back to the detection circuit, and from this information we were able to determine the conductance. So the actual mathematics of going from a change in detector voltage to a conductance is something we'll talk about in future videos. So what does a TRMC system look like in reality? Well, they're all home-built systems in generally, meaning you can't just contact a company and purchase one. So they all look different for that reason, but generally there's some sort of electronics inside of your system, and then there is some waveguide component because you need something to support the microwaves, the electromagnetic radiation, and then in addition to that you need some optical source to generate carriers. So in our lab at Oregon State University we have this big Faraday cage which contains the majority of the electronics and also the microwave waveguide circuits, and then we place the sample outside of the Faraday cage, and then we illuminate the sample with an optical laser. So this is a schematic diagram of a TRMC system. This is the system we have at Oregon State University. All systems are slightly different. Over the next couple of videos I'm going to go through I'm going to go through each of the different components in this diagram and explain step by step how they work and how we're able to carry out the measurement. But today what we're going to be focusing on is the microwave generation. And in our case we do that with what's called a voltage controlled oscillator. VCO is the acronym, and this is essentially just a signal generator. So in our case we have a VCO, voltage controlled oscillator. There are a range of different ways to generate electrical signals, and electrical signals in the gigahertz regime, which is typically what we're after for TRMC systems. We use something called a voltage controlled oscillator. It's a reasonably simple device. It doesn't have any graphical interfaces or buttons or anything like this. Basically what it does, it will output an oscillating signal, and the oscillating signal, the frequency of the oscillating signal will be linearly dependent on an input voltage, and typically that input voltage is called the tuning voltage. We're not going to talk about how VCOs work, we're just going to consider them to be some sort of black box that behave as we expect them to. So there are three terminals of interest to the VCO. The first is a supply voltage, which is just used to power the device and to generate the microwaves, to generate the electrical signal in the microwave frequency regime. Typically this would be something like 12 volts and a few hundred milliamps in terms of current. Then we have the tuning voltage, and this is a voltage, and the input here draws a lot less current, but the circuitry is designed in such a way that the output voltage, or the frequency of the output voltage, depends roughly linearly with the applied voltage to the tuning voltage terminal. And VCOs are designed differently, but for example you could have a VCO which accepts voltages from say 0 to 15 volts. That's typical. Then finally have the output voltage, which is just an oscillating signal. Both the supply voltage and the tuning voltage are DC. The supply voltage is absolutely DC and you don't really ever change it. The tuning voltage you may want to adjust as a function of time as you carry out the measurement, but generally you can still consider it DC. because for the majority of the time the input voltage is going to be constant. And the output voltage is going to be some oscillatory signal. You can picture it as being some sort of sine wave, and in our case the frequency is around 8 to 9 gigahertz. So if you were to increase the voltage applied to the tuning voltage terminal, what you would see is that the frequency of the output signal would increase. And when we're actually carrying out the time resolved microwave conductivity experiment, we don't change the tuning voltage, we keep it constant. We do need to adjust the frequency of the microwaves to tune the cavity and identify the resonance conditions. So typically the relationship is roughly linear between the tuning voltage and the output microwave frequency, but this is something which would have to be calibrated. And typically it's done with something called a vector network analyzer, where you put the output into this VNA, that's what it's called, and you'll measure the frequency as a function of input voltage. Generally, you only have to do this once, or occasionally periodically, just to make sure that the VCO is still calibrated. And once you have this information, then you can put it into your software to control the TRMC experiment, and the software will know for a particular voltage the VCO is going to output to a particular frequency, but this has to be calibrated. So choosing the instrument to supply the voltage to the tuning voltage terminal of your VCO is something which requires consideration. You can't just use a battery or an off-the-shelf voltage supply. To carry out these measurements, we need a voltage source with a particular set of characteristics. The voltage source for us is depicted in the top left of this diagram, just above the PC controller. Here I'm going to label it supply. For the purposes of this diagram, we haven't talked about the actual supply voltage which goes to the VCO. We're just going to assume that it's some constant voltage which goes via this control box on the right hand side. So when I label the instrument here the supply, what I'm talking about really is the voltage which goes to the tuning voltage terminal, and that's why it's connected to the computer, because we need to be able to control the voltage, whereas the actual supply voltage for the VCO can just be constant. So as I say, there are a few requirements we need for our supply for the tuning voltage. The first is we need a high accuracy in the output voltage. We haven't talked about it yet, but we'll come to it in a couple of videos time, that when you actually carry out the measurement, you need to identify the resonance conditions in the cavity. And what typically you're going to be doing is you're going to be measuring the reflected intensity back out of the cavity as a function of input frequency. So basically what we call a frequency sweep. And you'll identify at some point there's going to be this dip in reflectivity where the cavity is absorbing some energy, and this is the resonance conditions. And we carry this out in the dark without exciting the sample, just to identify when we have these standing wave conditions. But to do this, we need to be able to sweep the voltage, and we need to do it controllably in very small steps. So as you can see here, the frequency range we're actually looking over is only well, it's just under 100 megahertz. So you need to be able to control the voltage to a very high degree to be able to identify the different frequencies. So in particular, you have to have a voltage supply which is able to accurately output a voltage of, for example, 1 volt, and then a voltage of 1.0001 volts, and it needs to be able to separate these out because we're going to be having a very small window of frequency, but it could be a long way away from the beginning of the output frequency range of the VCO. So for example, you could have a VCO which outputs a frequency between, say, 8 gigahertz and 12 gigahertz, and we know that our resonance is going to happen around, say, 9 gigahertz, but we don't know exactly where. We may want to go up to 9 gigahertz, which means we're probably going to be putting in a voltage, say 2 volts, and then we want to sweep a very small region of frequency space around that, so we need to go from 2 volts to, say, 2.01 volts or something like that, in which case not every power supply is going to be able to do that. So this is something that you need. Secondly, you need the output to be stable over long periods of time. So as I said previously, you're going to be carrying out this frequency sweep in your instrument, and you're going to carry out the measurement on resonance. So in the example I've shown here, the resonance is around 8.58 gigahertz. So you'll carry out the microwave cavity sweep, and then you'll come back and set the frequency of the VCO to 8.53 gigahertz. Then you're going to carry out the TRMC measurement. But when you carry out the measurement, you're assuming that the frequency is not going to change, because you could be carrying out the measurement over long periods of time. You could have a low conductance sample, in which case you need to carry out lots of averages, or you need to carry out the measurement at various optical fluences, or wherever it happens to be. You may want to carry out a measurement over several hours. And if the frequency drifts, if the output voltage drifts, that means the frequency is going to drift, and it means you're no longer going to be on resonance. So that means the signal you observe in your microwave conductivity measurements is going to change as a function of time, and the assumptions you made about the resonance are no longer true. So this is something we need, i.e. we need minimal drift. And also we need a very low ripple voltage. We haven't really talked about this yet, but the TRMC measurement can be quite a low signal to noise measurement. It depends on the samples you're measuring, but if you have a very low mobility sample, the signal is going to be quite low. So what that means is you're going to have to average lots of measurements. So you hit the sample with a laser, measure the trace, and then go back and do it again. And typically you can do this, say 10 times to 10,000 times, but it all depends on the noise. And if you have a voltage which has some sort of variation as a function of time, I mean, all voltage sources will have what they call ripple, where there's this small variation in voltage. In our experiment, what that translates to is you're going to be at the bottom of this resonance, but you're going to be oscillating backwards and forwards slightly. As the output voltage changes, the output frequency is going to change, and then basically you're changing the resonance condition of your cavity. So when you carry out the TRMC measurement, you're going to have this variation in frequency, and the conductance that you measure is going to change as well. So what you need is for this to be as low as possible, which translates into lower noise in the actual measurement. So this is very important. Typically we aim for around 10 to the minus 5 times the tuning voltage. So say for example the tuning voltage is 1 volt, we'd want the ripple voltage to be around 10 microvolts or lower. So it's about 1,000th of 1% of the tuning voltage. And importantly, we need the voltage source to be computer controlled. In theory, you could sit at the instrument and sweep through from 8.4 gigahertz to 8.62 gigahertz by adjusting the voltage manually. But this would be incredibly time consuming, and if you plan to carry out multiple measurements, this is going to be prohibitively time consuming. So you need a computer to be able to control the voltage, and therefore to be able to control the frequency automatically and reproducibly. So in addition to having a voltage supply which is very low noise, we can actually go further. So when it comes to the VCO, we know that the supply voltage is constant. It's always going to be, say, 12 volts, and that's not going to change throughout the entire measurement. The tuning voltage we are going to change because we carry out a sweep, but after we've carried out the sweep, we're going to leave the voltage at the resonance condition and basically leave it there when we carry out the TRMC measurement. So it's strictly DC, but for the majority of the time it is DC. And what that means is we can then use filters because we don't have to change the voltage too often. So once we've found the resonance condition, we can pass our tuning voltage through a low pass filter, and that will basically remove any high frequency components to the tuning voltage. So say for example, we do have some noise on top of our signal. We know that the noise is going to have a certain frequency, and as if we have a very aggressive low pass filter, i.e. we remove all signals that happen to have a frequency above, say, 0.1 hertz, then cone that will reduce or remove a lot of the noise in our tuning voltage. So this is a way to improve the noise on the voltage further. One thing to be aware of, if your tuning voltage does go through a low pass filter, when you're carrying out the cavity sweep, you have to carry it out very slowly, because you could intentionally be changing your voltage, but because you're filtering it so heavily, the actual time it takes for the tuning voltage to respond will be quite long. Alternatively, you could bypass the filters where you're carrying out the sweep and then put the filters back into the circuit when you're carrying out the measurement. That's an alternative, but it requires more electronics and controller software. So the idea of filtering is to take a signal which looks like the following and then remove a lot of the noise. While there's still some noise, there's always going to be some noise, it's considerably reduced compared to the original signal. And in our system, that appears inside of the Faraday cage, but just before the VCO. So we have a filter box here, which is a combination of RC filters and inductive filters. So we have a supply voltage, which has a very low ripple anyway, but we want to improve it further, so we pass it through a filter box before it goes into the tuning voltage. So in our system, this is always in place. So when we carry out cavity sweeps, we do have to carry them out slowly. But the advantage there is we don't have to worry about switching the signal to bypass the filter. And finally, there is the issue of temperature stability of the voltage controlled oscillator. So the VCO, as I say, it outputs an oscillatory signal based on the input voltage, but because it's electronics, the temperature will increase as a function of operation time. So the longer the VCO is running, the higher the temperature, and it's going to peak depending on the model around 60 to 80 degrees Celsius. In itself, the temperature is not a problem. The problem is that the output voltage is also going to be slightly dependent on the temperature of the unit. And what this means is that if you initially turn on the VCO, it will output a certain frequency for a certain voltage, but as the components heat up, this may drift and you may get an unexpected output frequency. So we carry out the calibration when the VCO is hot. So the output frequency for a certain voltage is as if the instrument's been running for a long time. So this is fine, we can just turn on our instrument in advance of when we want to use it, and then everything should work as expected. However, there's one small catch to that, and that's that as part of the calibration of the detector, we need to measure the voltage output from the detector when there are no microwaves falling on it. And we'll talk about that in a little bit more detail in a future video. But what that means is we basically have to turn off the VCO, measure the voltage, and then turn it back on to carry out the measurement. So if we were to do this, remove the voltage supply, we may expect the VCO to cool down and then turn it back on, it will change. So you may get a frequency that changes a little bit when you do this. So for this reason, we just instead have a transfer switch in our system. And this is basically just a toggle switch, which is controlled by the computer. So the majority of the time, the default is for the VCO to output a microwave frequency, which goes into the antenna, produces the microwaves. And we'll talk about that a little bit in the next video. But when we carry out the calibration, we'll toggle the transfer switch and just send the microwaves to nowhere. The reason we do this is that we now have no microwaves falling on the detector, but we haven't turned off the VCO, so we don't have to worry about changes in temperature affecting frequency and so on. And for us, it's just the next component in line. The blue line there is the output microwave signal. It goes into this switch box, and there are two outputs from the switch box. The one on the left is going into the cavity, output 1, and output 2 is just going to nowhere. And then the black cable there at the top goes to the computer to control it. So thanks so much for watching. In the next video, we're going to be talking about the actual generation of electromagnetic radiation and the circuit, the waveguides and so on involved in moving the microwaves around our instrument.